Okay, I think we can go ahead and start the class. We are both live on Blackboard and YouTube. And again, we are eventually going to move away from Blackboard. So if you're watching these online, make sure to use the YouTube for the live streaming. So previous lecture, we talked about some mathematical backgrounds that just to remind you of some mathematical concepts that are going to be important in this course, like the divergence, curl, and the gradient. We are going to continue those reminders in this lecture, and we are going to build up on this to eventually find the governing equations. Not find the governing, I'm going to introduce the governing equations. I'm going to write them on the board, and I'm going to ask you to do the derivations yourselves. But before moving on, we need to talk a little bit about the divergence of velocity. So the idea was, when you have this del operator, dot product, another vector, you are taking the divergence of that specific vector. But divergence of velocity is very important in aerodynamics and fluid mechanics, especially low speed aerodynamics that we are dealing with. But in general, it is very important. What does it represent? If you recall the divergence of velocity, if you want to take this divergence, it would have been partial x, which is the x component of the del operator of u, plus partial v partial y, plus partial w partial z. So x component of the del operator multiplied by the x component of the velocity vector, y component of del operator, y component of velocity, and so on and so forth. But what does it represent? Why is this important in aerodynamics? Let's look at a fluid element. What does the gradient of velocity in x direction represent? This essentially means that for this specific fluid element, the velocity of this surface, let's say this is x, z, y. The velocity of this surface is going to be different than the velocity of this surface. So there is a gradient. There is a change when you're moving from this surface to the other surface, right? What does it mean? It essentially means you're pulling one surface. If you're thinking of a solid, if you think of a solid, you're pulling one surface more than the other one, right? So your volume is changing. Does that make sense? Okay. So, and then you're adding all of these changes in all directions together. So the divergence of velocity presents the time rate of change of volume, and we can mathematically prove this, and the proof is in your book. It is the time rate of change of volume per unit volume. Let me write it down on the book. Time rate of change of volume per unit volume. Okay. So let's say we are dealing with an incompressible flow. We know what an incompressible flow is. We have talked about it. and you have seen it in your fluid mechanics course as well. What is the value of divergence of velocity for an incompressible flow if we take this definition as a representation of divergence of velocity? This is what divergence of velocity represents. Time rate of change of volume per unit volume. This per unit volume part is just a normalization. We are normalizing the changes of volume. So this part is just nothing, right? It essentially represents the time rate of change of volume of a fluid element that has a volume of 1. Normalization. So what is the value of the divergence of velocity for an incompressible flow based on this definition? Think of a fluid element. Zero, right? Why? Because in an incompressible flow, the volume of this fluid element cannot change. So the total changes in all of the directions should be eventually 0. So if you're pulling it in the x direction, it actually has to shrink in the other direction, right? To compensate for that changes in the other direction. So for an incompressible flow, this has to be 0. Which is a type of flow we are going to see in low speed flights that have Mach number of less than 0.3. Any questions here? Okay. This is actually going to be a good segue to go to the governing equations we're going to see. We know there are 3 main principles that we are going to base our governing equations on. Conservation of mass is the first one. What does conservation of mass means for this small or big, whatever, for a fluid element, for an arbitrary fluid element inside your fluid? It essentially means that whatever is going in any other direction has to come out in another direction, right? Pretty simple. And if you, I'm not going to prove this. I'm going to give you the proof of the conservation of mass as a bonus point. The proof is in your book, so you don't have to do anything by yourself. I just want to make sure that you go over the proof. I may actually give you a homework problem. I have to think about it, but we'll see. So I'm just going to give you the final equation. The final equation of conservation of mass is going to look like this. Partial rho, partial x, partial t, sorry. Partial rho u, partial x, partial rho v, partial y, partial rho w, partial z has to be equals to 0. And it is not that hard to get to this equation. You can actually, if you write the conservation of mass in all of these directions, you will eventually get to this. Okay, let's say we are dealing with an incompressible flow. How can we simplify this equation a little? This is the general form of the equation. Yes. So density in an incompressible flow does not change, right? That's the idea. So this will go to 0. It doesn't really matter if you are in the steady state condition or transient. Changes of density is going to 0, and we can take the density out of these partial derivatives, right? And we have 0 on the other side, so we can essentially cancel density. So For an incompressible flow, you're going to end up with this equation, which is the divergence of velocity. Okay. We can have different representations of the same equation. This type of representation is something that is called the differential form of the equation, which essentially means that we have found the equation for a very small element of the flow. We can rewrite this differential form of the equation using different notations, using the del operator. Can rewrite it as well. We actually have an integral form of this equation, which hopefully you have seen in your fluid mechanics. I'm hoping. You don't need to memorize any of these forms of the equation. I'm just gonna write them down. So a volume integral of the changes of density with time plus another volume integral of the divergence of rho v is equals to 0. Okay, so conservation of mass. And you are going to get a bonus point if you submit the derivation for this. You essentially have to go to your book and follow what they have done. The complete procedure is in the book, right? So submit the derivation for this. For the rest of them, I'm going to ask you to do a homework problem, just to make sure you are familiar with the derivation. The derivations themselves are not important, right? It's just a mathematical operation. What I want you to understand from the derivation procedure is how to find an equation, how to find a governing equation for a fluid problem, which essentially boils down to conservation of mass, right? Just draw a fluid element, write the masses that are going in, that are coming out, and then find the equation, right? Yes. No. Start from a fluid element and find either the integral form or the differential form, right? So start from m dot out is equals to m dot in. Does it make sense? Pardon me? Yes, follow the textbook. And the idea is for you to understand that whatever complex equation we're going to get, we're going to have in aerodynamics, it starts from a very simple principle. It starts like this one. It starts from the fact that the mass is neither created nor destroyed, right? So m dot in, m dot out. Same is true for momentum equation. We start from the second Newton's law, F equals to ma, and so on and so forth. The same is true for energy equation. We start from the first law of thermodynamics. Okay, and based on all of those, you can find very complex equations that govern the fluid flow. So the derivation of this equation is going to be your first job, your bonus point for next week. The next equation is going to be based on principle of conservation of momentum. Conservation, not based on momentum equation. Based on the Newton's second law, F equals to ma, or sigma F has to be equal to ma. And ma is dv dt. This derivative refers to total derivative, or some people call it material derivative or substantial derivative. I think your book calls it substantial derivative, but in my note it is called material derivative. All three words are the same. But what is it if let me ask you, have you seen material derivative before in your mathematics or fluid? Yeah, one yes. Who hasn't done undergrad here? So you don't count. What about others? No? It's either yes or no, right? No. Okay. So we have to talk about material derivative. I assume up until this point, you have always calculated acceleration as derivative of this regular derivative of velocity versus time, right? But what I'm saying is that this is not a regular derivative, the acceleration. Acceleration is actually a different form of derivative called a total derivative. Okay? But what does the total derivative mean? That actually goes back to the changes you're going to get. You're going to have different forms of changes you're going to have over time, right? Let's think of this fluid element here in this coordinate system. Okay. Density of this fluid element can change, right? So it is possible for us to have a gradient of density with respect to time, okay? But let's say this fluid element is moving. There is a velocity here in this flow field, and it's moving. And it gets to a part of the region, part of your domain that has higher temperature. It is a little hotter, right? The density is going to change as well, but that change is not a function of time, right? It's a function of space, right? The density has changed because we have moved, right? It is a spatial change. Your book actually has a very good example, and I'm going to give you another example that follows the same logic. Let's say we're all here. Let's say they turn off the AC, right? Temperature is going to decrease. We are going to get colder, right? That's the changes of temperature with respect to time, right? We are not moving. We are at the same place, but the temperature is going to change. But think of another condition. The temperature, the AC is going to remain consistent. They're not going to change the temperature on AC, but the temperature outside is different, right? From here. So if I start moving from here to the outside, my body's temperature is going to change, right? And my move from here to the outside takes time. So that change of temperature depends on some time, but it's not, the temperature is not changing because of the passage of time. It is changing because of me moving. If during that time that has passed, I didn't move, my body's temperature would have stayed the same. Does this make sense at all? So we are talking about two different changes of temperature that, or any variable that can happen over passage of some time, right? A spatial change and a temporal change. Your total derivative is going to combine these two changes into one, essentially. So for the example of your acceleration, is changes of velocity with respect to time plus the changes of velocity or the velocity gradient as it moves through a space. Again, this part is referring to the spatial change, and this part is referring to the temporal change. Yes. I'm sorry. All of them has to be partial. Sorry. Then the question, so what would be the total derivative of density? So we understand the total derivative of velocity, but what would be the total derivative of density? The first part, the temporal derivative, partial rho, partial t. But what is the next part? I just want to make sure you can make the distinction between this and this. These and these. So these three are referring to the, yes. That is my mistake, sorry. Thank you. That is should be Z, yeah. Okay, let's go back to density. I want to make sure you understand the distinction between these. In a spatial derivative, there are two things that are going to become important. How fast you are moving to get to another point, right? And how much that variable changes as you move. Let's go back to the example of me leaving this room to go outside, right? My temperature, the gradient of changes, the changes in temperature in general over time is going to depend on whether I'm running or walking, right? So that's one thing. It is also going to depend on what is the temperature difference between the outside and inside. If we are in the summer, the temperature difference is going to be different than in the winter. Does this make sense? So how fast I'm moving outside is going to be this, right? So there will be always presence of velocity when you're dealing with total derivative, right? How fast you're moving, my temperature, my body temperature, okay? And then whether your variable is changing by itself or not when you are moving from one location to another location. Does this make sense at all? Yes? So can you tell me what is the derivative of density? Okay. How fast density is changing as you change the location is going to stay the same, right? So we will have a presence of velocity. What about the rest of it? How much density is changing as you're changing the location in each direction. So partial rho partial x, partial rho partial y, partial rho partial z. Starting with this acceleration example, it always is going to make it confusing because we are going to have two velocities. But the thing is, acceleration is the changes of velocity. So this part is talking about how velocity changes between two different points. This part is only talking about how fast you are going from point 1 to point 2, in which between the two, the velocity is going to change. Does this make sense at all? So let's do for a general alpha, like variable alpha. Let's call it alpha, whatever. What is the total derivative for this alpha variable? Anyone? Can you say it? Partial alpha, partial p. So the temporal change, right? Thank you. Okay. Is this clear? Material derivative. That's just another mathematical operation. Again, essentially with the first part of it, we are concerned with the transient changes. How much that variable changes at that specific point over time. Like let's say it is like heating up a pool of water, right? A pot of water, right? How much temperature is changing over time at that pool, right? But the rest of it, the spatial part of it, it is talking about how temperature for a pot of water is going to change if you move it from your kitchen to outside, right? I'm pretty sure you have seen this videos on YouTube that became popular like 2 or 3 years ago. I mean, they have always been popular, but they became very popular 2 or 3 years ago. That people went outside and just pour boiling water in like freezing air. Have you seen these type of videos? It just started instantly freezing. Right? That is your spatial. I mean, that is a representation of this spatial derivative, a combination of the two, in fact. But does this make sense at all? Okay. So we understand the total derivative. We understand the total derivative for acceleration. And let's go back to the momentum equation. The idea was momentum equation is based on Newton's second law. Let's talk about this right-hand side of the momentum equation first. M, total derivative of V with respect to T. This is actually, to be a little more accurate, we have to do this, total derivative of mv. mv is the momentum, right? The changes in momentum over time is equals to sigma f. That is the real representation of Newton's. That's the most accurate representation or most general representation of Newton's second law. Okay, so based on the definition we have had, what is going to be this total derivative with respect to time? The total derivative is always with respect to time, so it's going to be partial mv partial t, right, plus u partial mv partial x plus v partial mv partial y plus W partial mv partial z. Okay, so inside these derivatives, as you can see, we have a vector, a velocity vector. Yes. Yes, because in general case, your density is going to change, right? If you're keeping the volume constant, the mass inside that volume, the mass of that specific control volume is going to change, right? Or we can actually, to make it more similar, more familiar, we can just divide the whole thing by a volume and do a volumetric force on this side, right? Okay. You may notice here that I'm actually, in the previous formulation, we had partial u partial x, but here we have partial v. Here, I'm not assuming, I'm not making any assumption here. I'm not making any simplification. So I'm including the v in the formulation as well. This essentially means that other components of velocity can also be a function of x. But you don't need to like focus on it that much. So, or in another notation, we can actually say this is partial rho v t plus v del v. Or v dot del then v. It's the same thing. So temporal change, spatial change. So we have some solution for the right-hand side. Left-hand side, we need to go back to identifying the forces that are being applied on the fluid element. Yeah, sorry. Rho v here. Thank you. Okay, so we need to find all of the forces that are being applied to your fluid element. What are the forces that we are going to have here? In general, what are the forces that are being applied to a fluid element? Pressure and shear, we are going to have pressure force as well as shear force, right? So shear forces are present because of the viscosity effects. So F viscous plus pressure forces. Okay. Pressure forces are essentially going to be canceled out in all of this different direction if there is no pressure gradient. So if you simplify things, you will essentially end up with pressure gradient multiplied by the volume, but we have divided everything by the volume before, so we're just going to stick with the pressure gradient, and this is actually the negative pressure gradient. What else do we have? What other force is present here? Weight, right? This fluid has some sort of weight, and we're going to call that body forces, F of B. The viscous forces, let's not get into that. So in general, you're going to have this whole thing equals to the other side. This is going to be your momentum equation. Yes. All of these, yeah, we have taken volume of all of these forces. Yeah, but uh, in the equations you're going to use, we have already done this division, if you will. This is going to be your partial form, okay, your differential form. But if you take the integral with respect to volume, you're going to get the integral form as well. And you're going to get a homework question on the derivation of this thing, but you essentially start from there. Okay, is there any questions here? No. So let's see, what is the application of this momentum equation? That's a very complex equation. It doesn't really look very engineering-like, right? In engineering, we see most of the things are a little simpler, right? Well, what is the application of this in aerodynamics? When they first started, the NASA engineers, when they first started like normalizing or standardizing airfoil and airfoil analysis, they need to come up with a way. Let me clean this one. They needed to come up with a way to measure drag force and lift force inside the wind tunnel. Like they didn't have computers to do CFD analysis for them. They didn't have a lot of measuring techniques that we have nowadays. And back then, actually, NASA was called NACA because the S part refers to space. They didn't go to space. They weren't going to space back then. So it was called NACA. That's why if you have seen any airfoils, a lot of them are called NACA a number, right? Whatever number that is. We're gonna go. I have one page about these numbering schemes in the notes, but we're gonna go over them later in the class. So they decided to come up with a methodology that will help them calculate specifically the drag. The first thing you need to understand is what is the nature of the drag. Drag itself is a force. So to calculate that force, you need to use the momentum equation, right? Sigma F is equals to ma. So the first thing they did, they ran the wind tunnel, and they let it stabilize, right? They let it become steady, right? What does it mean? It means that the changes of velocity and temperature, the temporal changes are going to be zero. So each point's velocity is going to stay the same. So this part was zero. Okay. They were dealing with very low speed conditions, so they could safely assume the viscosity effects are not there. This part is also zero. And the drag force is essentially going to be much, much higher than the lift inside the wind tunnel. So the weight was also zero. A lot of simplifications until this point. But one thing that I want you to understand here is the fact that this momentum equation is a three-dimensional equation. It essentially means that this equation is three equations, right? Three different equations. So the NASA engineers had to come up with a way to simplify this a little bit because they wanted to come up with a simple equation. It's not actually, the equation is not that simple, but the simplest equation possible to calculate drag. Okay. So what they did was this. Let's say this is the wind tunnel. The first thing they did was to change the angle of attack, make very small changes in the angle of attack. Okay. And also, they started with thin airfoils. Okay. So the changes in the y direction the changes of momentum in the y direction became unimportant, and their contribution to drag became unimportant as well. But what about the z direction? What did they do to overcome the changes in the z direction? What they essentially did is a very interesting idea. They made sure that the wind that they are analyzing covers the whole wind tunnel. So the wind is coming. Let's say I am the wind and the aircraft, and the wind is coming towards me, right? They made sure that the wind goes from the wing that they're analyzing goes from this wall to that wall. What does this do? It essentially helps removing the three-dimensional effects from the tip of the wing. And we are going to talk about the three-dimensional effects later in the class. So they remove the importance of this and this. So you end up with only one directional momentum equation, which is essentially is going to be equal to the other side, whatever that is. So to calculate drag, to calculate the forces that are being applied to this, we removed all of the complexities, all of the problems, and it boiled down to two variables. If we can come up with a way to get the velocity profile here in the inlet of the wind tunnel and the velocity profile here in the outlet of the wind tunnel, and then subtract the two, you are going to find the momentum that has been lost through this equation, right? And that momentum loss is essentially your drag. Does this make sense? Yes? Okay. So I'm going to give you another bonus point because I don't have time to go over the derivations, is to derive this equation for drag. The derivation is also in the book, so essentially you have to go to the book and copy the derivation that is out there, that is written there. I just want to make sure that you understand whatever they are doing and the simplifications. And you will essentially, what's going to happen is that your drag per unit length, keep in mind that we have removed the three-dimensional effects. So we are dealing with a two-dimensional drag, which is drag per unit length, is going to be the integral from H to B, rho U2 minus U2 multiplied by U2 minus U1. U1 minus U2. Always make this dy. Because actually you're going to end up with this dy. So what does this equation tell us is that as long as you can get the velocity distribution here, and you can get the velocity distribution here, this equation, this integral, is going to give you the total momentum that has been lost to this airfoil in this direction, which is the drag force. This is the definition of the drag force. Any questions so far? Okay. So what should we do? Let's say you are the NASA engineer in the 1920s who's working on this, and you come up with this formula for drag. And you want to calculate lift as well. What should we do for lift? Keep in mind that we have made sure that the flow is essentially uniform. So we have one-dimensional flow. The velocity with u, that is our only component of velocity that is present, is changing in the y direction, right? So the changes of velocity is going to contribute, or the changes of velocity is going to help us find the drag, right? What can we do about lift? Okay, but it is really hard to like put a pressure measuring device in the 1920s that doesn't disturb the flow. Okay, you don't want to disturb the flow. I didn't hear you. On the so this the velocity lift is going to be your force in this direction, right? The idea is the velocity is not going to change between here and here, right? It is going to change, but not in the y direction. It is not. Let me actually tell you the answer. Whatever you are having, the pressure, if this flow is generating a lift, pressure at the bottom is going to be different, has to be different from the pressure at the top, right? Otherwise, there won't be any lift generation. There won't be any force that is moving this upward. Like otherwise, it will be just a simple pipe flow, right? The pressure here has to be equal to the pressure here. So for your lift, you have to calculate the, let's call this A, B, the integral of pressure at the bottom minus pressure at the top, and this one is the x from A to B. So you have to have pressure at each point. You have to measure pressure at each point, which can be done by any type of pressure measuring device, and then you should be good to go. Is there any questions so far? There is one equation that remains, the one governing equation. This is a very important equation, and we can derive that using the first law of thermodynamics. But I'm going to assign that derivation as a homework problem as well, because we don't really, in this course, we don't really use the energy equation that much. I just want to make sure you have seen the energy equation as a governing equation. And yeah, okay. Let's solve an example. I'm going to give you like a couple of minutes, 5 minutes to solve this example. This is an example that is going to help us understand the drag calculations a little more. And then we'll move on with the fundamentals. So we have this wind tunnel. You have airfoil that is placed here. We have the velocity distribution in front, u equals to u infinity. And we have the velocity distribution at the back. You have u equals to u infinity here, u equals to u infinity here. Then u is u infinity multiplied by y over h, u infinity, negative u infinity, y over h, because of the negative slope. And h here is this distance, which is equal to 25% of your chord length. We want to find the drag coefficient. What is the equation that you want to use? This limits of equation here refer to this and this. So B to H. Okay. So how should we calculate the drag here? One of the graduate teams who is going to work on this problem is going to use this equation a lot, hopefully, for their project. Okay, think about it. This is the equation we want to solve. Your drag is going to be the integral of rho u2 multiplied by u1 minus u2 dy. So changes of this d in changes of velocity in the y direction is going to be important. We can actually divide this whole thing to 4 regions because we have 4 regions of change, different things. 1, 2, 3, 4. Okay, which essentially means that we can have 4 different integrals here, right? We can apply one integral, this integral, to region 1, right? Region 1 is actually this whole thing, right? Region 2, region 3, and region 4. What will be the solution of this integral in region 1? U2 is equal to u infinity. U is also equal to u infinity. So let's say this is integral of from 0 to 1. 0, that's 25% of your chord length. Let's say your chord length is 1. So 0 to 0.25. What will be the solution to this integral from 0 to 0.25? 0, right? U1 and U2 are equal. What about region 4? 0 again, u infinity. Okay. What should we do for region 2? Which is going to be from 0.1 to 0.2. So integral from 0.25 meters to half a meters. If we assume your chord length is 1. We're going to have rho multiplied by u2. What is u2? Negative u infinity y divided by h multiplied by u1, which is u infinity, multiplied by, and it is minus a negative value, so it's going to be positive, u infinity y divided by h dy. You can multiply this whole thing, these two parentheses together. We can u infinity and rho are constant if we are dealing with the incompressible flow. Rho is constant, so we can take all of these out. We're going to end up with a rho u infinity squared, right? Because we can take a u infinity from here as well. Negative y over h multiplied by 1 plus y over h. Does this make sense? So I'm just going to write this here, 0.25 to negative 1 over y over h, 1 plus y over h dy. So what is the solution to this integral? You can just multiply this y over h by this whole thing here. It's going to be y over h, y squared over h squared. Integral of y over h is going to be y squared over 2h, right? And for the rest of it, we're going to have y to the 3 over 3h squared. And h here, again, h here is 25% of your chord length, which here we assume chord length is 1. So it's going to be 0.25 h. And this is for 0.1 to 0.2, which was 0.25 to 0.5. Okay, we're going to have the solution to this integral, only this part of the integral. Okay. You can do the same analysis for the third part, this part of the integral, and then you will eventually get the d prime. Okay. Let's do another example, and we are going to move on. Any questions? Yes. That's the idea. Yep. The next example is telling us that we have a two-dimensional incompressible flow. So 2D incompressible. We have the velocity components as negative ky. K is a constant, like it can be 2, 3, 4, 5, whatever. It's a constant divided by x squared, y squared, and y is v. Sorry, v is the component of velocity in the y direction. Is going to be positive kx over x squared, y squared. We want to prove, or this is the question, does this velocity profile satisfy the mass conservation for an incompressible flow? The first thing you need to know is what is the mass conservation for an incompressible flow? Anyone? We talked about it, right, in the beginning of the class. Mass conservation for an incompressible flow, or conservation of mass for an incompressible flow. Just read it out. Okay, so we are dealing with an incompressible equation. How can you simplify that? Exactly, and you can take all the rows out of the differential, take it to the other side. So essentially, you're going to have partial u, partial x, plus partial v, partial y, plus partial w, partial z equals to 0, or the divergence of velocity is 0, right? And we are dealing with a two-dimensional flow, so W, the third term, is 0 by itself. So a flow has to satisfy this condition to be incompressible. Okay, so as long as you understand this concept, the solution to this problem becomes fairly easy. You just have to take the derivative of u and v and then add them together. You should get a 0. If you don't get a 0, your flow is not incompressible. Do we need to take these derivatives? Is there anyone who doesn't remember how to take this derivative? Okay, that's good. So the next thing we want to talk about, we're going to start talking about flow kinematics, fluid kinematics. To understand fluid kinematics, we first have to become familiar with some terminology, like the streamlines, stream lines, path lines, and streak lines. Path line is a path a fluid particle goes through when it passes point 1. So let's say you have a fluid particle at this point, and then you want to see what is the path it has taken at after an hour. So a path a fluid particle takes after passing through a point. So the particle has moved from point 1 to point 2, right? If we are dealing with unsteady flow, path line for two different particles that are passing through the same point at two different times is going to be different because the flow is unsteady. So the forces that are going to be applied at this location is going to change over time, or partial rho partial t, partial whatever partial t is not 0. Does this make sense? Path line. A streamline, or let's talk about a streak line first. A streak line is a combination of all of the fluid particles or fluid elements that have passed through point 1 at a time delta t, right, at 1 second. Let's say after 1 second, 100 fluid elements have passed through this line. The location of those after this 100 second is going to be your streak line. So at time 0, let's say this particle, this fluid element passed through this point 1. At time point 1, this one passed through point 1, time point 2, point 3, point 5, until the present time. Okay, it's just a definition. A streamline is a line that is tangent to your velocity vector at all time. So if your velocity vector is changing, is moving, this line is also moving. And a streamline is a concept that we are going to use a lot in aerodynamics. What will happen is, if you are dealing with a steady state condition, with a steady flow, so the temporal changes, the changes over time are zero, then all of these three are going to essentially be the same for an steady incompressible flow. Okay, is there any questions about this definition? So let's focus on the streamline a little bit. The idea is that the definition of a streamline is a line that is always tangent to the velocity. Let's say we are talking about this point A, and then we are looking at a very small element on the surface of this streamline. Very small element, right? ds. Let's call it ds. What can we say? And this ds is essentially, let me actually try to make it a little simpler. Two different points on a streamline is S1 and S2, which has X, Y, Z, X, Y, X, Y, Z. Okay. The distance between the two is delta S, and it makes a border. As you move these two closer to each other, you're going to get to ds. It's still a vector, but it will represent a very small element on that curve. Is this clear? So that ds is itself a vector, dxi, dyj, dzk. So what can we say about these two vectors? The idea is that vector ds is always tangent to the velocity vector. Go back to the mathematical operations of vector, the vector calculus we just talked about in the previous lecture. What is the cross product between two vectors that are in the same direction? What is the cross product between two vectors for which theta is 0? 0. Now go back to the definition of cross product. Magnitude of ds, magnitude of v, sine of theta. Theta 0, the cross product is 0. So ds multiplied by v is 0. Okay. So if you recall, the cross product of ds and v in the Cartesian coordinate system was dx, dy, dz, u, v, w. This has to be equal to 0. This itself was a vector, and you will eventually end up with this w dy, v dz is equals to 0, u dz, w dx is equals to 0, and v dx, u dy is 0. So you're going to end up with three equations. This is essentially w dy v dz I plus whatever k, j, plus the k. And for this vector to be 0, all of these components have to be 0. Pretty simple. Okay. Let's say we are dealing with a two-dimensional flow. What is going to happen to these three equations if you are dealing with a two-dimensional flow? Can you speak up? That this is a very general formulation, so we didn't make any assumptions here. This will always be 0, right? That's based on the definition of a streamline. Okay. But what can you say about this speed? It should be 0, right? So 0, 0, which means that this udz is 0, vdz is also 0. So all of the changes in the other direction are essentially going to go away. And we are going to end up with this equation as the only equation. If you rearrange this, you're going to get dy over dx is equals to v divided by u. Okay, what does this mean? This essentially means that we can find the slope of a streamline by having the velocity component at each point, which essentially means that you can find the equation of that line by having this velocity component. Or if you have the velocity component, if you have the equation of the line and you want to, this is the slope of the streamline, right? We understand that, hopefully. dy dx is the slope of this streamline. Okay? So by having the velocity component in each direction, we should be able to find the velocity component. Is there any questions so far? Okay, so I'm going to talk about one more concept, or we can actually talk about it in the next lecture, but it's an important concept. It shouldn't take more than 2 or 3 minutes. Okay, let's do it. A stream function. So we have the streamline, and we can find the equation of that streamline using this formula. Okay. But we have another concept that is going to be very important in the future. So it's a very important concept. Make sure you understand this. It's called the stream function. The idea here is, let's say we have these two streamlines. Velocity vector is always tangent to this streamline. What does it mean? It essentially means that there is no mass passing through the streamline, right? Because velocity vector, that's the definition. Velocity vector is always tangent to the streamline. So there is no mass passing through it. So whatever mass you have here at point 1, you're going to have the same amount of mass here, right? Because you are not, these streamlines are essentially acting as walls. No mass is going to pass through them. That's the definition of the streamline, okay? So we're going to define this stream function. Let's call this psi bar. The mass of the potential of this streamline, the mass of at C2, and the mass of the streamline at C1, right? The difference between the amount of mass between the two lines, this is called psi. This is the Greek letter psi, if you don't remember. So the amount of mass passing through this streamline is essentially the difference between these two masses, which is going to be rho v multiplied by the normal vector to the cross-sectional area of that inlet and outlet multiplied by your unit depth, which is 1, right? That's essentially the mass, the definition of your flow rate. So the flow rate is going to change this much between the two streamlines. Okay. If you take this to the limit, which essentially means that if you make these two closer, what you're going to get is going to be this: partial psi, partial n is going to be equal to rho v. V. Okay. And this psi is a directional thing. It can have directions in x and y. So we can eventually have the two different components as this. Let's say we are dealing with compressible flow, incompressible flow. U is going to be equal to partial psi over partial y, and V is going to be equal to negative partial psi over partial x. Okay, so why is this important? Why is this definition important? If you have the stream function for a flow, you will be able to find the velocity distribution, which is a huge help, right? If you can have the distribution of velocity, you have everything. You should be able to calculate anything you want to calculate. And we also have this definition in cylindrical coordinate system. So VR is going to be 1 over r partial psi partial theta. And the theta is going to be negative partial psi partial r, right? Yeah. It's a two-dimensional case, so we are only going to have r and theta, right? A spherical and cylindrical coordinate system. Both of them will be represented by r and theta. Okay, so if we have the stream function, we essentially have everything we need to be able to calculate the properties of this flow. And that's it for today. Next week, we are going to hopefully solve some examples, and we are going to continue with the vorticity. And I think we are going to finish chapter 2 next week, next Monday. Do we have class on next Monday? When is the President's Day? Does anyone know? Is it next Monday? Yeah, so if the President's Day is next Monday, then it is a wellness day, and you can stay home and try to be well, I guess. It is a holiday. It is the 15th, Monday after Valentine's. So, yes, it's a welcome holiday.